Hi, I'm Brian Klamick. I'm here to talk about heaps and resources in DX12. I'll start with the basics. Starting since D3D9, almost everybody should be familiar with the concept of a committed resource. In DX12, we call them committed. What you're doing when you create one of these resources is you create both virtual address space and physical address space. Essentially, initialize and manage physical memory of a certain amount. Both of these units are together, essentially managed as an entity in a committed resource. But DX12 goes even farther. It allows us to tease these two apart and gives the application much more power when trying to manage physical memory. In DX12, we've got a heap API construct, and with it come two new resource types, the placed and reserved resource. It's worth noting that in DX11, the reserved resource existed as a tiled resource nomenclature. However, we haven't seen much adoption of tiled resources, so we'll be treating them as mostly new. In DX12, when you allocate a heap or create a heap, you are essentially creating the physical memory aspect of a committed resource. You should assume it has some size, like it's 5 meg entity, and there's such thing as memory segments in DX12 as well. This heap is either located in video or system memory. When talking about discrete adapters, of course, if it's a UMA adapter, it's always system memory. And you can also assign properties of, we call them CPU page properties, where you get to choose the CPU caching behavior if you give the heap CPU access. Giving the heap CPU access is equivalent to calling map in D3D10 APIs, or in D3D9 it was called lock. It's when you get access to a CPU pointer and the CPU modifies memory directly. Placed and reserved resources differ in that reserved resource has its own unique GPU VA space, and it allows us to allocate a large range of VA space up front, and then map VA pages to certain sections of the heap later, and then reconfigure that arrangement on the fly. Whereas placed resources are a much simpler design. A placed resource is really just a pointer to a certain region of that. For example, say we had like a 5 meg heap. I could put a placed buffer or a placed texture, like in this region, maybe this 1 meg, placed. So I like to represent this with an arrow because a placed resource is really just a pointer, as you'll discover, versus a reserved resource. Where you create potentially a really large virtual address region. We could even say this is like 1 gig. But I don't actually have to use 1 gig of physical memory. I can sparsely map this reserved resource. So assume this is a 1 gigabyte buffer, a reserved 1 gigabyte of contiguous virtual address space. But I'm allowed the flexibility to choose that this first 64K page points to here by calling APIs like update tile mappings. I get the ability to make this resource quote-unquote resident manually by changing page tables on the fly. That's how these all differ. I actually like to take a step back. Many people focus quickly on just heaps and resources when really applications are solving memory management problems. I like application developers to keep these things in mind. Like, what do we have in the marketplace in DX12? Of course, UMA versus discrete adapters. Even the discrete GPUs vary heavily in the amount of memory that they have available. Even the Surface Book these days, or that we just announced, has only 1 gigabyte of physical memory on the discrete adapter in the keyboard. When you're thinking about UMA adapters, like how much physical system memory is in a system, because essentially a UMA system with 2 gigabytes of system memory is really only going to have about 1 gigabyte of that available for a DX GPU usage. Another problem is variable demands on the system. DX12 forces applications to manage the amount of memory that they're using directly. GPUs don't support page faulting, so you have to be very conscious that on systems with only 1 GB, you don't overcommit. You'll find in the documentation we describe what happens when you do overcommit. Essentially, the OS has to freeze your whole process in order to switch to another process and allow that process to run. So it degrades. We're essentially scheduling one task at a time when you use too much physical memory. Essentially, this bullet is also trying to say that it can vary dynamically depending on what the user is doing, either intentionally or unintentionally in the background. Consider what your user is actually going to do with your game. If it's a racing game, it makes sense that the user is really going to be invested in racing around the track. But if your game's an MMO, I know that some system configuration sites, they rate the systems by how many instances of an MMO that they can run at a time. So consider how nice should your app play well with the rest of the system. Do you have to support side-by-side application, side-by-side, or your application being run side-by-side? Do you have to support scenarios where your user might switch to IE and watch a video on where the location is of every single collectible in the game, etc. Because if they start doing any sort of side activities, then your foreground application or the game is not going to have as much physical resources available to it, or physical memory available to it. And then, of course, I'm just calling out that DX12 has a lot of tiers in a bunch of different feature areas. So your game engine can get complex quite quickly if you're going to optimize for each and every individual tier. Do you want to have separate quote paths for UMA adapters versus not? Do you want to handle things differently if the system has more than 4 gigs of memory? Most developers I talk to, they like to start simple and then add optimizations later where it actually gives bang for the buck. Here's the bane of, I think, a lot of DX applications: the dynamic application budget for physical memory. If you don't know about this API, it's a good time to start learning about it. Again, if your system really only has a gig of video memory available, this is the API you come and ask, how much is available for me? Again, it changes. So you call this API 1 second, and it gives you a different answer 2 seconds later. There's 2 buckets, local and non-local. This covers discrete adapters as well as UMA. So on a discrete adapter, the local bucket is video memory and the non-local is system memory. On UMA, the non-local budget is always 0. So applications should start playing this level am I going to manage both budgets or just one? It is possible to just look at the local bucket as the memory that I'm going to manage, and then assume that the rest of the memory I do use is small enough to fall within the gaps, or maybe it's actually going to be a system memory bucket, or somehow assume it doesn't need management, or explicit management. Applications will get under pressure that they'll want to not just manage the amount of video memory available, but also the amount of system memory. DX11 apps there is no dynamic budget that they pay attention to. They already create lots of resources. So coming to DX12, they have to introduce this concept into the app, and then they have to start doing this long, arduous work of finding all the resources that they do use and better categorizing them. Now, essentially, there is a simple option here to try and manage one budget, but it has weaknesses when you're dealing with a UMA system. So imagine we've got a 1 gigabyte, or that the maximum amount of memory this API will ever return is a gigabyte. All heap types will come from that gigabyte on a UMA system. And I believe many apps will, or many engines will, prefer to think of things as a discrete adapter style. They'll be thinking that the local budget is video memory, so therefore they only have to care about the heap type defaults, being budgeted, whereas everything else they're much looser on. That's why I suspect some apps they'll probably start with one just to cut their teeth on the idea, but then they may just evolve to do 2 budgets over time, and understand how to deal with UMA versus discrete systems. I doubt many engines will just write a fully general physical memory manager. So I'm proposing that I suspect that this is going to be useful for applications as they port, that they'll want to categorize all the existing resources that were already created and classify them into these categories, and then try to move resources in heaps that were in a classification with a lower value to classifications with a higher value. Applications need to use memory just to draw a UI on the screen, right? That's what I'm suggesting that this classification is. There's a certain amount of not just resources in heaps, but a certain amount of D3D objects that must be created in order for the application to draw anything on screen. Of course, you'll need like a swap chain. You need some textures, depending on how you're doing text, like geometry versus just bitmaps. And all of those objects must be able to be created for the app to make forward progress. So in the DX12 model, if you create something like a heap, or you create command allocator, query heaps, command queues, like any physical memory that is required by that object, it is acquired and allocated during the creation of these API objects. If the application can't create those API objects, it'll fail and early out. And a basic problem of DX11 apps coming to DX12 is that every single resource you created in DX11 falls into this category. We happen to know that many engines happen to be creating or overcommitting a lot of memory in DX11 because you can get away with it. The OS memory manager will page things in and out for you. An application could create something like a 1 gigabyte resource that it never uses in DX11, but in DX12, that 1 gigabyte resource will it'll eat up that chunk of memory such that it'll always eat up that chunk of memory. Any other resources that are created later are at high risk of failing creation. So the second classification that applications want to think about as for how to manage memory is resources that can be scaled, resized, or optionally used. So we've got ideas of level-specific models and textures, right? Like you want to create these when the level is visible through a portal or when the user chooses a particular level. And then of course, you want to destroy them afterwards, because if you keep them created and you leak them, it'll erode into the budget that you can use for, the level that the consumers are really trying to use. One suggestion I have here is try to proportionally scale many of these resources. So if the application is creating a swap chain of 800 by 600, it doesn't make a lot of sense to create textures any bigger than that, right? Keep them smaller. Integrating this classification with the dynamic budget, you'll want to think about reevaluating whether certain resources are optional or not, roughly every frame. Committed resources are quick and easy, but when we created the Heap API, we looked at the most significant expense of creating committed resources in previous APIs, like DX11. And we found that managing physical memory was the most significant expense. So you'll still get benefits from using placed and reserved resources here by avoiding destroying and recreating the heap. But lots of factors play into this, like your placed resource can only be a subset of the heap size. Reserved resources aren't always available everywhere. These are just ideas to think about when choosing which type of resource to use for a particular texture. And this classification of resources is the reason we've introduced placed resources. Many rendering algorithms these days are like deferred rendering. There's multiple passes that occur throughout rendering. Some of the video memory that was used during pass 1 could actually be used during pass 2. This is like hard to pull off in DX11 because if you're using a texture, you have to make sure the format and dimensions were roughly the same so that you could use like a sub-region of the texture during pass 2. And it was like really messy because you had to keep sticking with an already created resource. But in DX12, I can create a heap. The heap can be about 10 meg. I can have a texture with one format using the same pages that another texture with a different format happens to be mapped to. The MSDN documentation describes how I can indicate or how I can switch from using two overlapping placed resources, an aliasing barrier that we have in the API that's required to call between these types of transitions. If you find the types of resources that are used and then used within one part of the frame and then not used during like a second phase of rendering, definitely look for placed resources to help here. You can still get the same benefits from using reserved resources, but again, reserved resources aren't yet available on all DX12 hardware. And the last classification I have is streaming resources. Example would be like an open world terrain. I think there's some DX12 demos where they show, definitely there's been games in the past where the games are loading textures either off the network or off the disk, paging them in maybe like one page at a time in order to maximally use the amount of physical memory. Ideally, applications will want to use reserved resources for these, but again, not all GPUs currently support reserved resources. Placed resources is a reasonable fallback. However, placed resources suffer from, they require being contiguous and fully mapped. Applications will likely be shuffling a lot or copying texture data around a lot when using a placed resource solution. I mentioned that there's a few heap types. There's one specific heap type that we have called heap type upload. The recommended heap type to use for uploading resource contents. However, there are some scenarios in which applications can do better on their own. So an upload heap is always in the system memory segment, regardless of UMA versus discrete. The pages are marked write combine on discrete GPUs and some UMA adapters, but there are some UMA adapters in the market where you'll find that the pointer is actually coming back with write back caching properties. In short, just use an upload buffer. We go into a description in the MSDN documentation in the programming guide where we've added new functionality to copy texture region that allows you to pack texture data contents into buffers such that you can use the buffer as a ring buffer and ask the GPU to copy from wherever the CPU put it into the final texture or a heap type default texture. So again, while generally we recommend you use big buffers big ring buffers to stream data to a GPU, this usage pattern is essentially working around the limitations of discrete GPUs. Discrete video memory, you can't access all that memory from the CPU. So that's why in DX12, when you create a heap type default, it has no CPU access. So instead, you've got to create a different type of resource that the GPU can access, stage the update with the CPU, then have the GPU relocate the data it can access into the final VRAM. On a UMA adapter, the situation is, or this pattern is much less efficient. The CPU can actually access all system memory, but there's still a lot of caveats associated with it. Like, I certainly don't recommend applications go out and recognize UMA and then set or use custom heaps in system memory with especially write-back properties. There's a lot of details, or I put a lot of details into the MSDN reference pages to help developers like find decent usages or decent optimizations for UMA. So I recommend going there. Essentially, some UMA adapters still want to be treated like discrete adapters. They still want their upload heaps to be marked write combine. So they benefit to some degree from an application still like teasing apart those things that the GPU is just going to upload, because you'll get a higher upload bandwidth through there. But there are definitely situations where there are UMA architectures on the market where creating a system memory heap with write-back CPU cache properties allows the CPU GPU to like start handshaking, like pass data back and forth relatively efficiently. If you're looking to get into those situations, like know that you're special casing, or you're taking the dependency on these types of architectures. It's not clear how well discretes are going to perform. So if you're interested in the functionality we have available for UMA adapters, there's doc pages associated with it. Some of the APIs we specifically added for it was the custom heaps, like the ability of applications to create heaps in particular memory segments with particular cache properties. We also did a feature for colloquially known as parameterized swizzle, where you can create a texture in system memory and call write to subresource. That method will use the CPU to convert from row major memory layout to essentially a swizzle memory layout. Applications like looking into UMA optimizations are also going to be interested in the standard swizzle feature we did. Like some adapters do support texture layout in a canonical swizzled layout, where we've gotten good alignment in the industry where they are evolving to support the standard swizzle memory layout, but the current support is quite limited. So the CPU can understand like exactly where the texel like 1, 2 is, and do interesting algorithms based off that. Any more additional questions? This is the end of my talk. Please leave us feedback on the forum. I did spend a fair amount of time polishing up the MSDN docs. Unfortunately, it was just the reference pages. So if you're interested in like resource flags, architecture capabilities, pros and cons of using one versus the other, the reference pages should be good for that now. Unfortunately, the programming guide is a little bit less polished. This talk should help mitigate some of that for now. Leave us feedback on anything else, and I'll talk to you next time.